Here's an example in which we're trying to see if there's a connection between driver age and number of driver deaths per 100,000. So you wish to determine if there is a linear correlation, a connection, between the age of a driver and the number of driver deaths. So the following table represents the age of a driver and the number of driver deaths per 100,000, usefulness level, blah, blah, blah. Okay, in other words, what we're saying is, as drivers get, younger drivers, maybe there's more deaths, or maybe older, like, drivers that are 80. Is there more, deaths because they're too old and they aren't competent behind the wheel? And then really young drivers, of course, they don't have a lot of really young ones here. 33 is about the youngest. There's no like 17-year-olds. So anyway, so we're looking and saying, is there a connection between the age of the driver? Like, as we get older, do we cause more deaths on the road? Or younger, do we cause more deaths on the road? Which one is it? Is there a connection between the age of the driver and the number of driver deaths? So this is a very important concept in the world today, in the 21st century, the information age. All the time, people are trying to figure out if there's connections, we call that a correlation, between two things. In this case, age of a driver and number of deaths. Insurance companies, medical health groups, people that are police department that's in charge of driver safety and stuff. Is there a linear correlation between age of a driver and number of deaths? All right, so how do we go about figuring that out? Well, this is on your notes. Let me show you. So here are the exam. This is the exam 4 notes. If you go on down to number 6, there it is, testing linear correlation. I've copied it over here. Let me just, I can write on it right here. So it's number 6, testing linear correlation. So put the data in L1 and L2 and then do this linear regression t-test. Okay, so let's do it. So basically, the first step is this is going to become L1 and this is going to become L2. So step number 1, put the data down L1 and L2. You know how to do that on your calculator, right? You go to Stat, and it's already, hit the Stat button, it's already on the edit. It'll be there automatically. Just hit Enter, and then go to the top of L1, press Clear and Enter. Go to the top of L2, press Clear and Enter. And then put the data down L1 and L2. Okay, so, and then once you've got that in place, step number 2, so that's what it says right here. I'm looking at the notes. So put the data down L1 and L2. Then go to the linear regression t-test. So that is on your calculator. Let me see where it is. Again, you're going to, you're going to press the Stat button and go over to Tests and go down, and it's all the way down there. It's usually F. Over here, let's put it down here. Go way down to, on my calculator, it's F, to the linear regression t-test, and hit Enter. So that's the test we want. When you do, what you'll get is the following information. It'll say the X list, the Y list, the frequency, and it'll say like a funny looking B, which is actually a beta, and a funny looking P, kind of like that, which is actually a rho. It's a Greek R. Anyway, and then they'll And so let's put in what we want. So for the X list, that's L1, Y list is L2. So we're basically saying this is L1 is X values and the L2 is Y values. Frequency is 1. That means just each of those entries only counts once. And then as far as this stuff right here, the B and the P, which is actually beta and rho, but whatever. What you're going to do is you're going to put whatever we have right here. So that's going to be, in this case, not equal. Now you might have greater than or less than or whatever. You just put whatever. See, we have this. This is a rho right here. This is a Greek. I keep calling it rho. So this funny looking P thing right here is a Greek rho, and meaning it's a Greek R pronounced rho. So why I'm even bothering to tell you that, I don't care that you know any Greek or anything, but I just want you to know it's the same as this R. So I don't want you to be confused. When you see the P, realize it's the same as R. It's just a Greek R. Even though it looks like a P, it's technically a Greek R. They call it rho, but it's an R. It's basically an R. So know that P, which is really rho, that's a Greek R, and then R is an English R, of course. And remember, have you noticed all the way through this course, whenever we have Greek letters and English letters, what's that all about? I don't know if you've caught it. We've done it a lot, but it's easy to miss it, you know. Greek is always about the true value, the true R for the whole population. And then over here, this, whenever we do English, it's the R value for the sample. The R value for, so R is the linear correlation coefficient. And so is rho. Rho is as well. Rho is just the Greek version. Now, if you noticed, maybe if you missed it, let me make it clear now. All through the course of statistics, whenever we have Greek letters, it's always the true value for the whole population. English letters are for the sample. What am I talking about? Meaning, we want to, R's the linear correlation coefficient, right? Remember when R's close to 1.0 or negative 1.0, that means they have a very strong linear connection. Whereas if R is close to 0, there's no linear connection, and if it's close to 1 or negative 1, there's a strong linear connection, right? Well, so why we're into that is we're going to calculate the R for our sample, for which means this is our sample, right? These are the whatever it is, how many drivers? I don't know, however many this is. For these specific drivers, we're going to calculate how well these values fit on a dot. You know, these are going to be dots. We're not going to bother to graph it, but if we graphed it, we would see some dots, and we would wonder, how well do those dots fit a line? Well, that's what R will tell us. How well this data and this data, if we bothered to graph it like over 35 up 20, over 35 up 20, dot. And each of these is a dot. How well do those dots line up? How well do they fit a line? That's what R is for our sample. For this group of whatever it is, 1, 2, 3, 4, 5, 6, 7, 8, 9 drivers. But why are we doing that? Well, because we really want to know about the truth of all drivers, right? We don't just care about these 9 people. We're not like, these 9 people, I just really, really, really want to know. But no, we want to know something about all drivers in the world, don't we? That's why we're doing this. We're trying to figure out, for everybody who drives in the whole world, is there a connection between driver age and number of deaths? Right? That's really what this is all about. We don't just care about those 9 drivers. We're using those 9 drivers to figure out something about the whole world. That's always what we're doing in statistics, right? Okay, so that's the Greek R. It's the true R for the whole world, the whole population. Right? That when we say whole population, we mean the whole world. So that's what. So in other words, we're going to let the value of R for our sample, for our 9 drivers, tell us something about what might be the true R, which we always use a Greek letter. We always use Greek letters for the true value for the whole world. What's the linear connection for the whole world? Is there a relation between driver age and number of deaths for the whole world? Or maybe the sample is just lucky, right? That's what it's all about. All right, hope you're making sense of that, and that's always all throughout the course. Okay, let me get rid of some of this stuff, and let's go on with the problem. So how do we actually go about testing that and figuring that out? Well, what we're going to do is we're going to fill in the information I gave you right here. L1 is the x values. L2 is the y values. Frequency is 1. This is not equals because that's what we're testing. If it's not equal to 0, if the true value for the whole world, right, that's the Greek R, that's rho, even though it looks like a P, and we're saying, is it really 0? Oops. Let me. Is it really 0? Meaning no linear relationship? Is the R for the whole world, the rho, the Greek P, really 0, or is it not 0? Is there some linear connection, right? Because if rho is 0, if R, that's a Greek R. If R is 0, then there's no linear connection for the whole world. There's evidence that there's no linear connection between driver age and death. Whereas if it's not equal to 0, then maybe there is a linear connection between driver age and number of deaths for the whole world. That's why we're using the Greek symbols here. All right, so find the linear correlation coefficient. So on your calculator, after you finish doing this, you go down and you hit calculate. It will tell you an R value. Roll on down. You'll find, so what I just got for mine, I got R is 0.99185. I don't know how many decimals they want. Oh, first for it there, 4, huh? So 99185, I guess we'll round that, 9919. And find the p-value. So let me see, the p-value, I got a p-value 0.0813 to 4 places, 0813, yeah, four decimal places. All right, so how does what was the test they wanted me to do? They want to say the p-value is, how does it compare to the alpha? That's the question. What was the alpha? Significance level 0.01, that's alpha. So the p-value is there. The alpha level is 0.01. So how does the p-value compare to the alpha? The p-value is greater, isn't it? 0.08 is greater than 0.01. So you know this thing. If the p is low, HO must go away, right? We've done that for all of our hypothesis tests. Is our p low? No, it's greater. So in this case, we're going to say if p is not low, the HO must not go away. In other words, we're going to keep HO, right? It's not going away. Tracking with me? Do that for all of our hypothesis tests. Our p is greater than our alpha level. Meaning they wanted evidence below a 1% chance luck, because that's the problem, right? You got some evidence that maybe the dots look like they kind of line up, but maybe this is just a lucky 9 drivers. Maybe we just got lucky and the dots don't really line up. The real truth for the whole world is no, there's no real linear relationship. Maybe you say, yeah, but I looked at 9 drivers and the dots seemed to line right. Our value came out very close to 1, didn't it? Pretty close to 1. So if you saw the graph, we're not bothering to look at the graph, but if we did, they would be pretty lined up because this R value is close to 1, which means pretty strong linear relationship. But maybe it's just luck. Maybe we just got a lucky 9 drivers, and really if we looked at more drivers, we would have found out that the dots don't really line up. They're actually all over the place. There's no connection between driver age and no linear connection between driver age and number of deaths. Maybe. I don't know. How do we know? What's the chance of luck? That's the p-value, right? Are you getting the hang of that? P-value is the probability of luck. What's the chance that we just got lucky 9 drivers? 8% chance. And they wanted evidence less than a 1% chance of luck. That's what significance level. They wanted it so significant that there was less than a 1% chance of luck. What did we get? 8%. Too high. So the p is not low. There's too big of a chance of luck. So HO must not go away, right? If the p is low, the null must go away. But if the p is not low, the null must not go away. We keep the null. So we're keeping the null. So we say greater than alpha. Do not reject the null. Do not reject. Now, I know you might think, well, should we accept the null? It's not really, we're not really accepting it. Why not? we fail to reject it. We fail to reject the null. Well, how's that different than accepting the null? Well, we are going to keep the null, that's true, but remember, it's like a court of law. The null is always what we assumed. We assume HO. And that's evidence, weak evidence. If the evidence is weak, we keep going with it. And that's our conclusion. You only go with H1 if evidence is strong. So it's just like a court of law, right? You assume the accused is innocent unless evidence is strong. So HO is exactly what we assume in a court of law. We assume the person is innocent. We assume HO is true. We assume, and what does HO say? That the P, which is the same as R, is 0, meaning there's no linear relationship. We assume there's no linear connection between driver age and number of deaths. That's what we assume unless evidence is super strong, below a 1% chance of luck. Well, evidence came in fairly strong, but there was still an 8% chance it could have just been luck. That's too high for us, so we say, nope, we're going to stick with our original assumption. But we're not saying we accept it. Just like when you don't convict somebody accused in a criminal case, that doesn't mean you're like sure they're innocent, right? You're not saying, I accept their innocence. I'm sure they're innocent. No, I mean, maybe sometimes, but usually it just means the evidence wasn't strong enough. They may have done it, but you're not comfortable locking them away when evidence is kind of weak. Evidence wasn't strong enough, right? So that's why we say we just don't reject the null. It might not be true. The null might not be true. HO might not be true. We just don't reject it. Why not? Because we fail to reject it. That's different than saying we love it and we accept it. We are going to keep it, but we assumed it's true. We're not sure it's true. We just assumed it's true. So what's our conclusion? Is there, remember up here, we say there is weak evidence, right? We're going with the null. Weak evidence. So is there, no, not significant, not, well then it's got to be this one. That was easy, huh? There is insufficient evidence to make a conclusion about the linear correlation between driver age and number of. Yep, there's just not enough evidence. There it is. So we have got it. So there is the question.